Morten, thanks for coming today. You just landed straight from Billund, which I think is where Legoland is, right?
That's correct.
So the best place to start with, and then coming to Oxford University to talk about design of experiments. You're giving a workshop tomorrow in the morning on statistics, design of experiments for scale-up.
Yeah.
So really looking forward to this. And today we're going to chat a little bit about your background, what you do with DOE, and how that fits into the scale-up story. So take it ahead if you could introduce yourself.
Yeah, sure. Thanks for having me. My name is Morten. I'm a chemist by training. I have a PhD in inorganic chemistry about a decade ago now. And then for the last 8 years, I've been working at the Danish Technological Institute, where my job is essentially being a statistics consultant, both internally. So we run a lot of R&D projects in the field of green chemistry and recycling technologies when it comes to chemical recycling of materials, but also sort of directly facing customers, helping R&D departments in various companies learn how to use DOE and other relevant methodology to sort of accelerate their R&D work. So
Amazing.
That's what I do.
Yeah, I mean, cutting straight in there. So you have a chemistry background, but now do statistical consulting. How was that transition?
It was gradual. Going back all the way to my PhD, I spent a lot of time coding for data analysis. So as I made the transition into industry, a lot of my work was doing custom analysis. At that time, I programmed in MATLAB. Since I've made the transition to Python, Python wasn't a big programming language a decade ago. It was just starting out as a thing. And then I transitioned into industry, did a lot of data treatment there as well. And then I think it must have been 6 or 7 years ago, I was working on an R&D project in the wood coating space, you could say. The kind of company who makes the stuff that is on top of this table and on wooden floors and so on. Traditionally, they've been made using harsh chemicals. And this project was about making the transition to water-based coatings. And so that was a classic, chemical product development problem. And we spent the first year of that project doing experiments in the lab in the usual fashion, which it means changing one thing at a time and doing experiments in a very wasteful manner. And after a year of this 2-year project, a year into it, we had done, I think we tested something like 200 different coatings in the lab and got nowhere. And it was right after summer holiday, one of the first weeks coming back after summer holiday. I didn't really know what to do with my time. And there was a book sitting on the shelf of one of my colleagues that had been recommended to me on design of experiments. And I opened that, and that was sort of, the start of a pivot of my career. Because in that project it was then obvious we should apply this way of experimenting. And after having read through that book and played around with some software, we did a DOE design for this project and managed to get from scratch, because we had gotten nowhere, to a finished product in 30 further experiments after having spent a year doing 200 and gotten nowhere.
Wow.
And that was what got me hooked on working with these methods. And I wish I had known sooner, but there's nothing to do about that now. Yeah,
well, better later than never, right?
Yeah, exactly.
So, that's a great story. So we're obviously going to have a lot of chemists tomorrow, and we ask participants when they apply for the C to kind of tell us where they come from. And I can already see that design of experience is not the primary focus in a chemist's teaching and learning. Mm-hmm. What do you think? How is it that we can change this? Maybe how can we get more DOE, more statistical thinking into chemists and biologists and people that need to work with experiments and do science?
Yeah, it's a good question, and I'm unsure sort of at what level of education we should put our effort in, because I think most people actually meet the concept of changing things one at a time to learn about baking or chemistry already in basic school, in something like the 7th, 8th, 9th grade, when you begin to have more of the sciencey classes. That concept gets introduced. Then you move on up to high school or whatever the equivalent is in the country you live in, and in the natural science courses there, it's still change one thing at a time. That's sort of the prevalent message for how science is done. And then once you get to university, everybody knows this as a truth and accept this. And it's never questioned again. So one could argue that you should just, fix this at the university level, but I think there might be some reason to also considering whether there should be political lobbying towards changing the curricula of at least high school when you get to the sort of higher level science, chemistry, physics classes there. So that's sort of about where to attack the problem. In terms of how to attack the problem, I am unsure. Because I guess it's going to depend on the political structure of the university you're trying to fix this at.
Yeah.
I think, it's important to consider that a tool like design of experiments is a tool. So it should be taught like a supporting thing you have to know when you are going to be a chemist or when you're going to be a molecular biologist or whatever. And if you do such an undergraduate program, you will have certain basic courses that are not, within the core of molecular biology, but you will have to take some math classes. And if you're studying physics, you will have to take some, you'll have to take calculus and so on, because they are supporting tools that make you a better physicist or a better chemist. Mm-hmm. And I think it's important that DOE is taught in a similar way, where the materials you use to teach the method are close to the field, which means that the curriculum has to be adapted to each individual, undergraduate program. Like exercises that make sense for physicists are not going to be the same as exercises that make sense for biologists, for instance.
Yeah.
And this is one of the barriers for changing, because you can't do a one-size-fits-all solution like you could do with a calculus course. Like it's more or less the same macro. At least at the university I attended, it was the same for everybody, right?
Yeah.
But when you get to DOE, it has to be close to home, and that requires resources. I think what you shouldn't do is let a mathematician teach it. There's, at least in Denmark, there's a propensity towards, if we have a math course, it's somebody from the math faculty who will be teaching the methods there. If it's linear algebra, it's a professor in that field who is going to be teaching that. But for a tool that is meant to be applied in the actual lab practical work, I think it's very important that the students can see why it's going to be useful to them. And maybe also sort of expect them to integrate it in their work as they, have courses that fall later in their graduate or undergraduate program than the DOE course, whichever course you sort of weave that into.
Yeah, I think it's interesting that you, of course, say the student, should be able to see why it's good. But of course, we have whole industries, pharma, chemistry, biology, where there are people right now spending millions of dollars running experiments, many of those not with any DOE in mind. So, of course, the question is, should we retrain and so forth? But we're going to leave that out for now.
Yeah.
I think we probably both maybe see more hope in a new generation maybe that will come along and bring the DOE by default from a university mindset. But
it's certainly easier, right?
Yeah.
If nothing else, when you are a student, you are in your only job is to learn, right?
Yeah.
And you are in a learning state of mind, and you are open to ideas being pushed on you. Like once you make the transition into industry, irrespective of the industry, your main task is not to learn anymore. Yeah. It is to apply.
Yeah.
Right. So it fits better in the university system.
Which, of course, that's one angle, one direction. But we have one topic, which is why does academia not prepare you well enough for industry? So. Mm-hmm. Does our conversation fit into that, or would you add a few more things? What does academia lack on top of the DOE to get you into industry and really make a change and difference?
So I think, at least now, I can only speak sort of from a Danish academic perspective, because that's close to home. But I think we've sort of, at least in Denmark, gotten to a point where an educational direction like chemistry has sort of become over-specialized, in my opinion, especially, or at least at the undergraduate and master's level, or bachelor master's level. Because once you leave academia, most of the extremely specialized courses that you have over the course of a master's degree, you will never use again. But what you will use again and again and again are sort of the broad skills, like being able to handle data treatment, being able to have a holistic understanding of chemistry or biological systems or whatever. That will be generally useful, and also across a relatively wide range of industries, being able to think critically and so on. And these, you could say these broad, unspecific skills are very useful in industry. And then the sort of the subdomain that a specific company works within, they will have to teach you the ins and outs of that anyway once they hire you. And that's going to be true no matter whether you go into a company that produce yogurt or medicine. Right. The specialized knowledge there will be taught to you after you start.
So you send over a map of DOE or DOE map, which I thought was really interesting. I see here models, Bayesian optimization, Brownie Bee. We're going to see Brownie Bee tomorrow at the workshop. Quality measurement as well. So tell me more about this map. How did it come around? Does it help you structure your thoughts? What's the background?
Yeah, so I made it after I had stumbled upon, I don't remember if it was a blog or a YouTube video or something that sort of spoke about the positive sides of using mind maps to sort of like build an overview of concepts and ideas. And then I decided to apply that to DOE to sort of try and sort of group things. And it's a fun exercise actually when like making this, it made me really realize that I've learned a lot of stuff in this field because you just sort of like empty your head and sort of begin to put things out with enough space, and then you group things that are related to them. So when it comes to things like quality measurements, for instance, once you begin talking about that, it's natural to think about things like noise. It's natural to think about how do we define quality, and then you sort of move on from that in a way. So that was sort of how this came about as I trying it out.
I do it myself. I have it's in my PhD for any topic. After a year or two, I would sit down and be like, okay, but how do these things connect? I think it's a great idea. One thing I see here is quality measurement. It's actually just with Jasper just now, we talked about that. And I think you're a prolific LinkedIn poster. And I think one of the lessons you posted once was that kind of like a pass-fail measurement is pretty useless. Of course, once you have maybe a range of outcomes, so this is a high quality, low quality, even then, if noise is particularly high on an outcome measurement, how we're going to do good science is a big question. So what do you think about quality measurement? Is that something that you think is very much undervalued?
And it's one of those difficult problems where there's sort of a bias against doing anything about it. I think it's the sort of the illusion of clarity. You could say that as long as you don't have to put quality into operational terms by defining sort of the whole process of actually turning quality into a number, then it's easy to feel like you know what quality means. And as long as you feel like you have it in hand, there's no reason to do anything about it, right? And that's all well and good until you get two people who feel that way, but when it comes to you get these two people talking about quality, you find out that they disagree. And I think that is just sort of bringing that bias into the light is one of the first positive effects of making sure you try to define quality in a way that you can measure, because it forces you to specify how you're going to measure it. And it will, like putting that in writing will make it very difficult to have different ideas of what that actually means in practice. So that's sort of the first step. And it's sort of underappreciated in many companies, I would say. Like a part of becoming a more digital company today is about turning things into reliable measurements, and putting numbers to things that are reproducible and so on. And measurement systems and measurements of quality sit at the core of that.
Yeah, that's I personally think really important. Definitely, of course, from statistical theory, we can very easily show that noise is a killer when trying to fit models. And I think oftentimes, I personally think that, instead of doing ever more smarter statistics, design, or theory, just get a better machine, a higher resolution, a better microscope often can already change so much in an experiment.
Yeah, and learn measurement systems analysis. That's again a thing that's not really taught in the sciences, because when you're a student, every measurement system you meet is as part of an exercise, and for an exercise to be useful, it has to work, right? And that means that somebody has done the measurement systems analysis for you. So whatever you're measuring, whether you are doing a small scale organic synthesis or growing some bacteria or something, somebody has checked that it's going to work and it's going to produce signal and so on. So at least the chemists will think that, it's everything measures perfectly, and so why should I care about the measurement system?
Right.
It's at least chemists have a tendency to think in those terms.
Yeah.
And that's fine at university, but it gets you into trouble once you begin working in a field where nobody has done measurement before. Yeah. And especially in an R&D context, at least we encounter this often, that you have a hard problem you're working on, and you are trying to make a process work to produce an outcome that you want, and you want to make progress towards that. So you need something that can measure progress towards it. So you need the quality measurement. But at the beginning, you don't have a quality measurement, and you don't have anything producing signal, in the sense that there is no quality at the beginning because it doesn't work right. That's why you're developing it. So in that is really a minefield, because when you try to develop a measurement system in that kind of environment, when you don't get a signal, is it because the equipment is not working, the measurement system is bad, or is it because there's still no signal?
Yeah.
Right.
Yeah.
And sort of untangling that can be a real barrier to progress. But most chemists will have a bias towards blaming, it's just a process, because we're not used to thinking in terms of the measurement system being at fault, which means that it can be at fault for quite a long time before you go and check and figure out then, that was the problem.
So measurement systems, is that something we would be able to see tomorrow in the 2-hour section, or is that already maybe beyond the...
No, I've deliberately made the choice of not overcomplicating the amount of stuff I'm trying to shove into the 2 hours I have tomorrow. But I've made it a point that is sort of on the top of the further reading recommendations to get a grasp of measurement systems analysis. And I mean, I will talk about why it's important, and even though it's not very difficult to do a measurement systems analysis, but for tomorrow I would much rather just focus on the DOE part and sort of getting them to get hands on that, and sort of hopefully kindle a little bit of a fire in them, because that's more difficult to pick up.
Absolutely, yeah.
Once you sort of get a little bit of a, if you get hooked on DOE, then you will measurement systems analysis will become obvious to you, and you will see the need for it everywhere. So I'm trying to target the hard problem tomorrow.
Yeah, and I think that's why we put that into the morning as well, because people still focused, and available. Yeah. And in the afternoon, we're going to have a bit more relaxed. So, of course, measurement system is one extended topic. Then human nature is another one. So I think you also written quite extensively on that. But here's a quote: "Most yield problems are human problems, but not technical ones." So how does that resonate with you? What are kind of the top 3 annoying human things that prevent you from doing a good,
So I guess sort of the bias of sort of being confident in a process that is bad.
Yeah.
Like sometimes it's called the Dunning-Kruger effect, right? At least the popular culture version of the Dunning-Kruger effect is that it's primarily stupid people who don't know how stupid they are. Once you begin to learn something in any field, you realize how much you still have to learn, right? And for most developers and scientists, DOE sits squarely in the area of you don't know what you don't know. If you couple that with many years of experience, then you can become very confident in a way of working that is not very effective. That is a human problem, right? Sort of the illusion of clarity is another human problem, like not realizing that there is an issue because your processes are sort of flexible enough to sort of wipe away the misunderstandings. So you never realize that there's a problem. And then sort of when it comes to the industrial application of these things, you also run into the sort of the very normal human problem of different departments having different prioritizations and incentives. Yeah. In the sense that in production, their main goal is to ship product out the door. It's not to learn anything, right? Nobody should touch the process because when it works, you don't touch it, and then you ship as much product as you can because that's what makes you money. You have that on the one hand, and then you have the R&D department whose job is essentially to invent the process and product of the future. But oftentimes in many industries, these two things merge a little bit, and R&D ends up doing a lot of troubleshooting in production, and R&D also ends up doing a little bit of sort of process development and recommendations for the running production. And there it will be natural for the R&D people to apply their learning-focused tools like DOE. But you can forget about getting a production manager to agree to setting the process to extreme values, and sort of the prioritization of that, because running experiments in such an environment is really expensive. So there's a risk involved in it as well, and that's difficult to deal with because you have different incentives for those departments, right? Yeah. Those are some of the first sort of human problems that come to mind for me.
Yeah, and I think that's again something we're probably not going to really touch upon tomorrow, because we're taking a kind of collaborative approach, and we're trying to like network and have people come together and first figure out the technical things, and then the question of what's the incentive structure. I think that will naturally come into it anyway, but we really do need some foundations on the DOE, and then also some ideas of like where has scale-up worked, where has it not worked, and then really the general things between biology, chemistry, and so forth. So with that, what's the scale-up challenge that crossed your desk the first time, and how did DOE play a role in that?
That's a good question. So we do a fair amount of scale-up in the projects that we do. I think, are you sort of familiar with the technology readiness level scale?
TRL.
Yeah.
That's the NASA scale anyway, right?
Yeah, there's like levels from 1 to 10, right?
Yeah.
And in this framework, universities have a role to play from 1 to maybe 3 or 4.
Yeah.
And industry doesn't really want to touch anything until you get it to sort of 7 or above. And what we do is typically in the middle. We start where a university group might have gotten a chemical synthesis to maybe like the high milligrams or maybe a gram of something. Then we have to take it from that to kilograms or hundreds of kilograms.
Right.
There are many things that become difficult once you have to make that sort of transition, because there are certain things about chemical processes that depend on the size of the system, and like the most obvious to everyone will be sort of heat transfer, and because you can see that on your stove at home. And if you have a very big kettle of water, like heat comes in at the bottom, and it's going to take a long time for that heat to rise to the top of your pan or whatever. Whereas if you have a very small, a metal shot glass of water, the heat will transfer up through that into the liquid very quickly because the distances are shorter.
Right.
And as chemists, it's not something that we are sort of taught to consider when we work in a lab. Because we work at a scale where everything is fast, mixing is fast, temperature transfer is fast. And once you get to a bigger scale, this is no longer the case. So if you're working in an environment where you have to scale things, you have to be very careful that you don't over-optimize the small-scale system, because the settings that work for making 2 grams of bread are not going to be the same that work for making 2 tons of bread in a process.
Right.
There's not going to be a one-to-one sort of correspondence between those things. But the underlying sort of chemistry is not going to change. And that means that the factors that are important for making it work, the things you have to tune to make the process work at the small scale, you are also likely to have to tune when you go to the bigger scale.
Yeah.
So if there's a narrow temperature window for your chemical synthesis or for your bacteria to grow in the lab, then you also probably have to control temperature once you get to the big scale. Mm-hmm. But you will have to do it in a different way, and the set point for your temperature in the tank might be different from what your incubator was in the lab, right? So in a scale-up context, it's much more about learning which handles are important rather than the specific values of the handles. And I think it takes experience to know that sort of, you have to change your focus to sort of learn what's important, what affects the underlying process, because that will be important at scale, right. Rather than sort of over-optimizing. Mm-hmm. And DOE is good in that framework because, one of the nice things is that sort of DOE forces you to consider sort of how much should something affect a process before I care about it. Mm-hmm. And you can sort of force your experimental work to just identify those things, the important ones for later, yeah. Right? Yeah. That's one thing. The other thing is that as you scale up, sort of, you could say that logistics become much more important and much more of a barrier. Mm. So again, it's easy to move things around when you just have a small flask of something. It's easy to add things to it. It's easy to store it and so on. But once you begin to get to sort of the high kilograms or the ton scale especially, it's not trivial to move 2 tons of liquid around. You're not going to do it yourself. You need machines, you need pumps. Things take up space. And sort of heat transport and so on is much slower. And so the logistics of handling things and doing that in an economical fashion become part of the problem.
Right.
And again, things that don't really matter at small scale, because at small scale you don't have to consider sort of the cost of moving the liquid into the flask. Right. Because we pay the PhD student anyway. Yeah. Whether she does it fast or slow, it doesn't matter. Right. But that's no longer the case once you get to much bigger scales.
And I think you just mentioned the economics of it, but is that we build a DOE understanding. We build understanding through DOE in the small scale. We don't want to over optimize, but we want to support learning, such that the core factors when we go on a bigger scale are still available and understood for us to optimize over. Mm-hmm. But then the logistical challenge means that we need to think about the economics of it now. So is there basically a need kind of to integrate maybe economic constraints in the DOE model, cost constraints or these kind of things? Have you considered that?
Yeah, and again, you have to be careful that that you don't consider the exact economics of the small scale too much, because you're not going to be running this process in the small scale. And things are much more expensive at the small scale. This is why you're scaling it in the first place, is to bring the total cost down. Right?
Correct, yes, yes.
But it certainly pays to sort of keep in mind the things that will drive your cost once you get to scale. And when you get to scale, it's going to be energy input, and it's going to be raw material costs, and it's going to be labor. and capex. I mean, getting the equipment needed to do those things, right? So again, things that you're not taught to consider at the small scale level. And I mean, there can be vastly different costs associated with, different approaches to drying a product. Even though at the small scale it doesn't matter, again, because cost is not a factor there. But when it comes to, evaporating water from things is some of the stuff we use so much energy for in our production systems. It's just removing water. And there are many ways of doing that, but they are certainly not, priced equally depending on your energy costs.
Yes. There's a quote here. It says, if it doesn't scale by a 10x range, it won't scale by a 1000x range. This, of course, depends on how you define scale, but what do you think of that?
So in the sense that if it doesn't become more economical by going to a bigger scale, then it's also not going to become economical by going to an even bigger scale. Yeah, maybe. I guess it depends.
Right.
On things like, which is a cop out. But I guess it is true. I mean, the important thing about scaling up is that the problem is not going to become simpler. That's the main thing. I mean, that's also why you would prefer to learn at the smaller scale, because it is cheaper to do so. And if you can rule out a bunch of things that are not important at the small scale, it's much cheaper to learn that at the small scale, and then just once you get to the big scale that those things are not important. And the new things that enter the process in terms of sort of like how you actually build this thing and how you get heat transfer in and how you mix this solid into this 2,000 liter vat of liquid and so on, that will introduce new things you have to care about, like how fast do we add this thing, how quickly do we heat it up so that the local temperature right around the heating coils doesn't kill all our bacteria, for instance, but we get the thing up to temperature as fast as possible. That's a trade-off that's only relevant for the big scale, because at the small scale it's fast, right? So you will be facing more learning problems once you go to the bigger scale, but there's a bunch of potential learning problems that you can eliminate at the small scale by the learning about the things where you can sort of transfer the knowledge to a certain extent.
So summing it up shortly, really then you need that DOE skill, because how else are you going to summarize your learnings?
Yeah, exactly. And I mean, it's mainly about having an efficient way of digging sort of through the highly complex problem and sort of sorting out the typically relatively few things that are important from the many things that are not, but that you can't tell in advance.
So I had a fair share working with Danish scientists now in my time, and I think there's something unique about Denmark. I'm going to call it the Danish factor now, but I think speaking to you and also other scientists in Copenhagen and Aarhus, there seems to be a bit of more long-term perspective, a bit more patience, a bit more tolerance to, maybe the unexpected things in life. Do you think Denmark has maybe like a special position in science in general, because maybe you guys are more relaxed, or?
I don't know. At least, I mean, some of the things you say at least make me think more of our tendency to be very pragmatic. As a culture, we're a pragmatic bunch. But we're also sort of a get things done and move on, like goal-oriented bunch. I mean, it's similar to German culture in that when we have business meetings in projects and so on, like we won't talk about personal stuff. We will just like go straight to the point. If we don't think about it. So, and once we're done talking about the project stuff, then the meeting ends and we log off Teams and then done deal, right? And it's quite different from many other cultures in that way. But sort of being pragmatic and realistic when it comes to both technical matters, but also many other things in life is, I would say, a relatively typical Danish trait, right? it also makes, as a general thing, we as a culture we don't we frown upon sort of over optimism and overselling of things.
Okay.
Like those things are tied to being pragmatic.
Right.
And that has advantages and disadvantages, right? The advantage is that, we can typically accomplish what we say we can accomplish, but it also sometimes makes us a bit too risk averse. Like if something is too out there or too radical of an idea, we will certainly not be first movers,
right,
as a culture, right? And then on top of that, there's huge personal variation, but I think that's a thing you will find in most Danes.
I think that's a very balanced take. Tomorrow, our workshop, it's wonderful to fly in someone from Denmark, and for you to share about your experience in DOE. Is there anything?
Thank you for inviting me.
Yeah, absolutely. It's a pleasure, and you're the headliner in the morning for sure. In the afternoon, is there anything that you're looking for specifically that's going to be interesting to you?
I'm mainly looking to help our participants in any way that might be useful to them.
Yeah.
That's what I'm here for and what I'm motivated by. I like working with technical things and I like working with DOE, but what drives my work in it is sort of helping others pick up a useful tool.
Yeah.
And it matters to me personally to sort of help make their lives easier.
Yeah.
That's sort of the driving force for me. And so I look forward to sort of getting to know our group tomorrow and sort of figuring out, okay, what is the best way, like with the, I won't be spending long time with all of them, but some of them I'll, join their group for, some of the other exercises and stuff we'll do. And my focus will mainly be on sort of trying to understand their context and sort of providing guidance towards things that might be useful to them, because I enjoy that process. And then I look forward to sort of, learning some of the things that the other speakers will be bringing, because that's also fun.
Yeah, no, it's great. I think in the afternoon we're going to be very collaborative, so I think you're going to slot in there very well. It's like we don't have a speaker-participant separation, it's a whole group, and some of the people have some things to share because they already have that experience. Mm-hmm. Okay, is there any other things you would like to talk about before we come to the final question?
No, nothing comes to nothing comes to mind particularly.
We'll probably do a second episode after the workshop. Maybe in a couple of weeks or months or years, and then we'll see maybe if some new questions have come up. But I guess my final question is there any question that you have for me?
That's a good question. I would be interested in hearing your perspective on sort of how to integrate statistical tools and statistical thinking in teaching.
In teaching?
Yeah, I mean, like getting it into the core curriculum, as we spoke about earlier. I elaborated quite a lot on my take on it, but what do you think is the most sort of realistic way towards making a change in that field?
The realistic way, I think what really resonated with what you said was it's about the language. So when you said, we have to show to the chemist very differently than to the physicist or the biologist, it's because they all speak a different language. Mm-hmm. So while it might sound like we're repeating the same thing 3 times, in fact, we're not. We're speaking in 3 different languages, and the mathematical core is the same, but the implications are very different to biology or chemistry. So having worked on the whole range, actually, alloys, biology, chemistry now, biology has more noisy systems. You're dealing with a fundamentally different problem. And so DOE there will be fundamental smaller examples that will be the same, but so I definitely resonate with it needs to be tailored and it needs to be that language. We can't expect everyone to learn statistics, we just can't do that. But what I think we can expect everyone to understand that one fact at a time is not a long-term solution, and that can be done in an hour. But being in Oxford here, the amount of scientists that I meet that that say, yeah, no, I'm just optimizing my system. And I'm like, how do you do it? And they're like, I just like change one factor at a time. And they don't even know it's a paradigm that's not good. But they use the phrase because it's so natural to change one factor at a time. It's problematic. So I think it's more for me about just getting the intuition first. So, what are interaction effects, and I think there are great tangible ways, in games even to suggest that, and it's nothing complicated, and it's really something that can be small stakes. And I do with all things that need a big change. I think it starts with a small change. So we need to make a small change that creates, a big lever on people's outcomes. Well, it's probably no accident that there's a workshop tomorrow.
Yeah.
Because that is our first change here. So we're setting the seed that then grows on, and we have 20, participants that will take this back into the labs, and they will challenge the people around them with like, you're doing one factor at a time. That's awkward. Don't do that.
Yeah.
And I think that will hopefully create a little bit of a first wave, through which we then can create, a bigger momentum. And then through that, I think through that kind of like strategy, we will then actually learn what kind of materials we should prioritize first. So I think this, design of experiments thinking should start in high school. I think there's no reason why it shouldn't. I think it
because like conceptually it's not difficult math.
No.
Not at all.
No. And you can show it in a 3D plot and a 2D plot, and you can 3D print little games. I think you 3D printed something. Like there's in principle no excuse why we shouldn't be doing this right now. But I think it should be part of the fundamental curriculum, and but we need to showcase that first, and there's a finite amount of teaching time, right?
Yeah.
So what else? What are we going to kick off the table so we can put the DOE on it? That's kind of a political thing, right? It's an incentive question. So I think starting small, creating that momentum around it will eventually, and this is a statistical way of thinking it, right? We're doing one workshop tomorrow. We're going to measure the impact of that. We have a form. At the end of the workshop, we're going to force everyone to fill it in. It's going to be 10 minutes of silence, and either you fill it in or you just twiddle your thumbs. But we're going to get that form, and then from that, we're going to iterate. We're experimenting to understand, okay, why was the DOE part in the morning so hard? How can we make this easier? What do you need more? Is this going to make a change to your lab efforts and so forth? And I think through that we can create a kind of momentum around this, and then people will start telling you as well, I think. And the answer is that that if it's supposed to happen, then it will, and if not, then we're going to have to readjust. But at least we'll get the measurements from that. And I think if we do then get to the point where we can provide different materials for physics and biology and chemistry, I think that's already a huge success as far as I can see. Again, I don't expect any chemist to pull up a statistical software and do these things on the regular. Yes, I think in the pharma industry at a high level, when you have lots at stake, I think that should be done. But like, most people will go through a whole bunch of training before they arrive at that stage. And I think creating a more powerful funnel to support everyone, it just has such obvious advantages for the whole industries, whether you're in pharma or just working on the plastics or whatsoever. Like, I fundamentally think telling people that there are interaction facts is such a powerful thing just for life. It should be really seen this way.
You can't unsee it once you see it, right?
Yeah, it's really hard. And then once you learn about step functions, like that some physical systems don't go linear, but they're like, it's like, oh no, like I can't, like, this is pretty. So anyway, so this is my approach. So it's not so much of like, what should we do specifically in detail? I think it's more, what kind of strategy for change are we going with? And in a way, that question is actually pretty great, because this is why the workshop exists. Because of this observation of like, we need to start a step shift here. And what's the smartest way to do that? And so that's why it's great to have the support of Jesus College, with the room, the space, and to fly people like yourself in here to make that first step. And then really excited to see where we're going to be in a year or two with this workshop. So
likewise.
Yeah, I think it's a good place to finish here for now, and I'll see you tomorrow.
Thank you for having me.
Thank you.